Hello, 大家好，今天我们 today we will talk about lecture 7, composed pendulum applications. For composed pendulum application, we will talk about the situation like simple compound pendulum. So we will go through the example to know about what the example is like. Task first read the general differential equations of motion for the pendulum figure 5.68 and determine its undimensional frequency for small motion about the static equilibrium position. The solution we will talk about, we use the moment balance equations for the free surface. For the free body diagram, the moment equation is I 0 times theta dot will equal to sum of the momentum. And when sum on the right side, right hand times applies because the moment is acting in the minus theta direction. For uniform bar, I0 is ml square over 3. Hence, the governing differential equation of motion is ml square over 3 times sigma dot. For GL m equals 0. From the simplify, you can get that the equation of that would be theta dot dot plus Cg over 2L. And that's for a uniform bar, I0 will equal, okay? And for small, at this situation, the pendular sigma angle is so small. So for small motion, we would take the small angle rules and theta approximate theta, and the nonlinear differential equation reduces to theta dot plus 3G over 2L theta. So we simplify it with the formulation, okay, and compile the pendulum and addressing equilibrium general position with coordinates of free body diagram. Because what the compile means, the compile is used to distinguish the present rigid body pendulum from the simple pendulum oscillation 3.4b, which consists of a particle at the end of a massless string. The differential equation is the rotation among analog, what's the analog mean? The analysis is, okay, of the single degree of freedom, displacement, vibration, power as delta plus omega m square is equals 0. The compound pendulum is natural frequency is the value we have calculated up. And we assuming the pendulum is released just at theta equal to radians is equal to 90 degree. Define the reaction force components O theta and OR as a function of theta only. So from figure 5.16c, applying the total force is equal in RG. RG total is the acceleration, right, in polar coordinates for the mass center of the road gives. The force balance will equal, because seeing the coordinates, you will find that we're using the theta r coordinates. And I think it's very important to know how to set up the coordinates. But here has a too different for me, so I could not really explain why it draw like this. But you should know. You can ask teachers or students later or for internet. The sum of the force, okay? And here we're using the yes, the knowledge we have learned about in our lecture 2. For the sum of the theta in theta direction, it will be this way. In the acceleration terms, rg dot will equal rg dot will equal 0. Because rg, what is the rg? Sd is the radius. Is equal L over 2 is constant. In equation 5.62, define the reaction force components, both r and O theta, but not a function of theta amount. Direct substitution from equation 5.60 into the second of equations, define with zeros, as O theta equal W times sine theta plus ML over 2 times theta dot. This is the equation we get from the upside, okay? And next we will see about how to find a comparable relationship. For OR is more complicated because the first of equations, 5.62 involves theta dot square. We will need to integrate the differential equation of motion via the energy integral substitution to obtain theta dot square as a function of theta, proceeding from theta dot equal. This is the energy duration, so you should take some notice with this. Okay, you should be notice about this. Multiplying through by d theta and integrating both sides of this equation will give such equations. So theta dot square over 2 is minus theta 0. So it will integrate from 0 theta 0 to theta dot. And theta dot square over 2 equal 3g over 2l, the cosine theta, 3g over 2l cosine theta. Substituting this result into the first of the equation gives OR equal W times cosine theta plus ML theta dot square over 2 equal omega times cosine theta plus ML 3g over 2l cosine theta equal 5W cosine theta over 2. This result shows that the dynamic equation force will be 2.5 times greater than the static weight when the row reaches its lowest position, theta equals 0. So let's talk about alternating motion equation with moment about g. Suppose that we have chosen to take a moment about g. The mass center of the road in figure 5.63, obtaining the sum of the moment of mg equal, this is the moment equation, right? So the moment has a negative sign because it is acting in the minus theta direction. In this equation, the required moment of inertia about g is ig equal m square over 12. Substituting for O theta from equation 5.63, we give such equations. So this is the take the rules, take the it is show you how to get the inertial, how to get the required moment of inertial. Or WL over 2 sine theta will equal ml squared times 1 over 12 plus 1 over 5 theta total equal ml squared on 3 over 3 theta total. Write the moment equation about 3 involves more work, but gets the same equations. Note that in the intermediate steps of the equation parentheses, that we are accomplishing the parallel essay formula in moving from Ig equal ml squared over 12 to I0 equal ml squared over 3. Here IO equal Ig plus MBGO squared equal Ig plus M half L squared, where BLGO is the vector from the mass center G to the pivot. Deriving the equation from the motion, from the energy equation, there are no external time varying forces or moments, or no energy dissipation. Hence, mechanical energy is conserved. T plus V is so much, okay?
Sorry, let's continue to see about deriving the equation of motion from the energy equation. There are no external time varying forces or moments or energy dissipation. Hence, mechanical energy is conserved. Let's using the energy equation. T plus V is equal to T0 plus V0. The meaning is the potential energy and the kinetic energy. Using a horizontal plane through the perpendicular V pivot point as a denton for gravity, potential energy gives V equal Vg equal minus W L over 2 cosine theta. For rotation about the fixed point, the kinetic energy of the perpendicular is defined by T equal I0 theta dot square over 2 equal ML square over 3 times theta dot square over 2. Hence, ML square over 3 times theta dot square over 2 minus W times L over 2 times cosine theta will equal T0 plus V0. And finally, it will equal 0 minus W over times L over 2 times cosine theta 0 equal pi over 2 equals 0. So finally, theta dot square equal 3G over L cosine theta. Differentiated, right, theta gives ML square over 3 times D theta dot square. This is the derivation, okay? For theta dot square plus mgl over 2 times sine theta. Finally, we can get the sine equation. But it seems that the first one was more easier, I think. Let's see the static stability about equation points. So finally, we get the equation like this one. Equilibrium for small motion about the equilibrium position, theta equals 0. So small motion about the equilibrium position, theta equals 0 gives the linearization differential equation of motion, theta total plus 3G over 2L times theta equals 0. For the initial conditions, theta dot 0 equals theta dot 0 and theta 0 equals theta 0. The solution to the linearization equation 5.61 can be stated by this one. Theta t equals theta 0 times cosine omega nt plus theta 0 dot over omega n times sine omega nt. Omega n will equal square root 3G over 2L. So consisting of a stable oscillation at the natural frequency, hence theta z equals 0 is said to be a stable equilibrium point for the body. So let's say equilibrium for small motion about the equilibrium point position theta equal pi. Motion is governed by the nonlinear equation of motion. Theta total equal minus 3G over 2L sine theta. Expanding sine theta in a Taylor series about theta equal pi gives sine theta equals sine pi plus sigma theta equals sine pi cosine sigma theta plus cosine pi sine sigma theta. Okay, and retaining only the linear term in the above equation and substituting back into the equation will give such equation. This is the small theta angle. So observe the negative sign in the coefficient for sigma theta. The solution to equation 5.69 for small motion about theta equal pi would be sigma theta t equal a1 times e to the omega nt minus a2 times e to the minus omega nt. The first term in this solution grows exponentially with time. Hence, any small disturbance of the pendulum from the equation position theta equal pi will grow exponentially with time, and theta equal pi is a statically unstable equilibrium point for the pendulum. Recall mass spring systems and comparison. Both negative sign would be simply a negative stiffness yielding an unstable system. Okay, let's see a swimming plate problem. So as you can see, the coordinates and the moments balance the force balance. The plate has mass m, length 2a, and width a, and is supported by a frictionless pivot at O and a ledge at B. The engineering tasks associated with this problem follow. Assuming that the support at B is suddenly removed, carry out the following steps. First one, the governing differential equation of motion. Second one, develop the relationships that define the components of the reaction force as a function of the rotation angle only. The third one, read the governing differential equation of motion for small motion about the plate's equilibrium position. Determine the natural frequency of the plate for small motion about this position. So let's see the figure explanation. Rectangular plate supported at O by a frictionless pivot and at B by a ledge. Thus, B free body diagram that applies after the support at B has been removed. So kinetics. Theta is in the free body diagram defines the plate's orientation with respect to the horizontal. The angle alpha lies between the top surface of the plate and a line running from the pivot point O through the plate's mass center at G, and is defined by alpha equal tangent minus A over 2 times A. So we can get a value. Then let's using the moment equation with moments taken about O. So IO theta dot equal the sum of M O Z equal WA square root phi over 2 cosine theta plus alpha. The distance from O to G is A times square root phi over 2, and the weight develops the external moment used acting through the moment arm of A square root phi over 2 times cosine. Then you should know that this is very important because in some calculation you will find that it's a little different. The moment is positive because it is acting in the plus theta direction applying the parallel. As this formula gives IO equal IG plus MBGO square M over 12A square plus 4A square plus 4A A square over 4. So substitution gives the governing differential equation of motion will be something like this. You should rewrite it by yourself because this is the practice from previous example, and we have complicated task A. To define the reaction force, we need to state the sum of force equal m times RG total, and the polar coordinate version of this equation works best for the current problems, and the free body diagram has been drawn using the polar coordinates with OG aligned. Okay, so this is what you should understand. And with the radial acceleration components of G. And all theta is aligned with the circumference components. That theta equals theta plus alpha be the rotation angle from the horizontal of a line running from O through G. For the equation components, the sum of force is W times sine theta plus alpha minus OR. So you can use in the fourth equation at r direction and theta direction. R dot equal 0 because r equal a times square root phi over 2 is the constant. Theta dot is 0, so theta dot and eliminate theta dot by substitution, so we can get the equation is W times cosine theta minus theta plus alpha, like this. This result is that all theta starts at W over 4 cosine alpha 4 theta equals 0, and it's 0 when the mass center is directly beneath and pivot point O. Theta plus alpha is equal pi over 2. To obtain theta dot square as a function of theta, use the energy integral substitution to integrate equation starting with this. Theta dot equal d over d theta times theta dot square over 2 is equal 3 square root phi over 10 g over a cosine theta plus alpha. Multiplying through by d theta and integrating both sides of the equation, we give such. This is the same as before. Let's substitute this result back into the first of equation 5, we gives OR equal omega times sine or theta plus alpha plus mx square root 5 over 2 times 3 square root 5 over 5 g over a sine theta. Okay, something like this. And task B is complicated. The equilibrium condition for the pendulum is obtained by setting the right-hand side of equation equal to 0, obtaining by theta total equals 3 square root 5 over 10 g over a cosine theta over alpha is equal to 0. So to get the governing equation of the motion for small motion about the equilibrium condition, start by substituting theta equal to pi over 2 plus sigma 2. So we can obtain the small theta, expanding the last term to on the right in a Taylor series gives such equation. So retaining only the linear term in this expansion gives the linearized differential equation of motion. As you can As you can see, the omega square. Okay, alternative developed for motion about equilibrium. Tasking movements about in figure gives I times sigma total equal the sum of MOZ. So task C is already complicated. You should notice the tool and how it, and I will talk about that. How you choose the coordinates. You choose the coordinates at this fixed point, not the center point. Okay, let's see next. Deriving the equation of motion from the energy equation. Energy is conserved, hence T plus V equal T0 plus V0. Using a horizontal plane through the pivot point as the denton for gravitation potential energy, we give this formula, and substituting this, you give this. Rectangular plane supported at O by a frictionless pivot and at B by a ledge. Free body diagram that applies after the support at B has been removed. Okay, has been removed. Oh, zone record. We can see the zone record to see how it's introduced. Okay, it's very interesting.